Well, hello everybody, Mr. G here today to talk to you about a different kind of energy we haven't talked about yet, this idea of thermal energy. And if you take a look at the background image, that should certainly lead you into what we're talking about today. We're talking about this idea called heat. But before we talk about heat, we should really talk about the difference between heat and temperature. People tend to use these terms interchangeably. So when we talk about thermal energy or heat, we're really talking about the kinetic energy, the total kinetic energy and stored energy within a given object, as opposed to temperature, where we're talking about the average kinetic energy of the particles within an object. So if we talk about an idea like a pot of boiling water versus an iceberg, if we talk about the pot of boiling water, the initial idea might be, oh, well, there's clearly more heat, but that's not true. Definitely more temperature than the iceberg, but in this case, if we look at the total amount of kinetic and stored energy within an object, the iceberg is just huge. There's just way more particles in an iceberg than in a pot of boiling water. Therefore, there's definitely more thermal energy in the iceberg, but when we talk about the temperature, the choice is clear. Let's take a look at this now at the microscopic level. And things that we know about objects now are that they're definitely made up of atoms and molecules, and these atoms and molecules are always in constant motion. So if we think about the idea of a solid and a liquid and a gas, when we think about what a solid looks like at the microscopic level, it's certainly this idea of all the atoms being nicely compact together and not very far apart and as close as they can. We talk about these ideas of lattice structures. We talk about this idea of just being very, very tightly compact. Now, if you've ever been on a busy subway train, then you know that when it's super busy, you don't have a lot of room to move. You still can move, but there's not a lot of room to move, so there's not a whole lot of vibration. However, if we move up to the liquid level now, you can think about liquid now as a substance that has a little more space involved now, where there's a little more movement possible, certainly a little more. So this would be like a morning, really, really early morning train where everybody else has gone to bed or hasn't woken up yet. There's your liquid. And of course, the granddaddy of them all is this idea of a gas, where we have so much space we don't know what to do with it. We're in the beautiful open field of science and running around and really enjoying ourselves. We can move any which way. It's beautiful. The question might be, what the heck is this guy talking about? Well, when we actually deal with thermal energy and this idea of a change in temperature, as we increase temperature, generally speaking, what's going to happen here is that the molecules are going to start to move faster, which would make sense. We're starting to infuse it with more energy, which means there's going to be more movement, there's more kinetic energy. Things are going to start to space out a bit, and the result is going to be expansion. Anybody that's done a chemistry lab involving heating knows that if you heat something up, it's going to change from a solid to a liquid to a gas, and in the process, it's just going to take up more space. So all of these ideas are at play when we're dealing with thermal energy. Now, if we wanted to take a look at an object being heated, there's really a couple of ideas to consider. And for those of you going on to do substantial work in thermodynamics, these are going to be crucial in your question setups. And it's the idea that really there's two things that are occurring as you heat up an object. And the first thing that's going to happen, of course, is as you heat it up, there will be an increase in temperature. The second thing that's going to happen is there's definitely going to be a change in state. So if we take a look at this is definitely water. And at minus 50 degrees Celsius, we definitely know that this is frozen. We know that the freezing point of water is at 0. So you'll notice that when we heat up the ice up to 0, something magical happens right here. It levels off for a little bit of time, only because we're starting to change state. There is a required energy to change a state from a solid to a liquid. After which time, look, now we're going to start to warm the water all the way up to the point where, again, at 100 degrees, where water boils in the Celsius scale, all of a sudden we're going to level off again because the water can't get any hotter, because what's happening? We're in fact changing over to steam. So there are these processes that occur, both temperature increase and change of state, both of which in more advanced thermodynamics is certainly something to consider. But either way we look at things, we always talk about heat as a flow from a high to a low concentration. And there's really three different ways for heat to be transferred. The first one is this idea of conduction. And you think about conduction as this idea over here with the hot poker. There's certainly some kind of contact involved between the two objects. There's an actual touching taking place. The second idea is definitely called convection. And convection is something that actually occurs in the sun to transfer heat from the core up through to the surface of the sun. And it requires some kind of movement of a fluid. Now, we're using fluid in its most general definition. Air is considered a fluid in this case. So again, if there is air convecting, then there's definitely going to be temperature changes. We hear about this on the weather all the time. The third one is this idea of radiation. And this picture shows an excellent example of that. The idea of heat being given off of an object and actually radiates through a given space towards you. There's definitely no medium required. If you think about the heat coming from space, the light coming from, well, the heat coming from space, it's going through a medium of nothing. There is nothing in there for the most part, which means that radiation is taking place just through empty space. So these are your three different ways of having heat flow from one object to another, and this is going to occur until thermal equilibrium is achieved. And for those of you that have forgotten what equilibrium means, obviously it means that the temperature of both objects balance out to be the same. So if we take a look at the amount of heat transferred, we can use some pretty fancy physics to deal with this, and it's this equation right here, that our change in heat energy, or just heat, is equal to mc delta T. And in this case, delta E sub H is again the change in thermal energy, which is also known as heat. M is going to be the mass of our object, and it's always in kilograms. C is a new constant called the specific heat capacity. And nicely put, the specific heat capacity is just the amount of heat required to raise a 1 kilogram object up a temperature of 1 degree Celsius. So we'll show you some standard values for that in a second, but it's definitely a new topic for some of you. Delta T in this case is going to be, as usual, our change in temperature, and we're going to deal with this in degrees Celsius. So when we talk about specific heat capacities, they are constants depending on which substance you use. Here is a few of the common ones that we're going to use. Water is certainly one that you want to know. Would these be given to you on some kind of equation sheet or constant sort of thing? Of course they would be. So never expect that you're going to have to memorize these. You'll always have some kind of access to this. So let's take a look at an example where we actually have to calculate the heat. And let's say I make a cup of coffee by boiling 250 grams of water. That is initially at 15 degrees Celsius. How much heat is needed? Well, again, we know that our change in thermal energy, which we're going to start labeling as Q. Okay, so I want everybody to realize that the original equation I listed was delta E sub H, but now we're going to start using Q to make things a little easier, and that's equal to mc delta T. Well, if we start plugging in our values, we know that our mass has to be in kilograms. And we know that the specific heat of water, as listed previously, was 4,180 joules per kilogram degrees Celsius. And our delta T, well, this is interesting. It was initially at 15 degrees Celsius, and it's taken up to boiling. And we know again, on the Celsius scale, that taking up to boiling means 100 degrees Celsius. So our final temperature minus our initial temperature. And if you do all the math right, my friends, you should end up with something around 89,000 joules. So again, for the most part, these are plug and chug type equations. You just need to know what some of these terminologies mean. Certainly boiling would be one. And of course, knowing the specific heat capacity is certainly useful. Let's do a question that seems inherently slightly harder, but is really not that bad. A 35 kilogram child goes down a 3.2 meter high slide. The child is initially at rest and moves at 1.8 meters per second at the bottom of the slide. If the slide is made of 12 kilograms of iron, I'm going to underline that, and all heat is transferred into the slide, by how much does the temperature of the slide increase? Well, that's crazy, because now all of a sudden we're dealing with changing energy type situations, but now we're actually going to bring in heat. You may recall with conservation of energy, we really left heat out of the discussion. So if we draw our picture, there's our slide right there. There's our happy little child at a height of 3.2 meters. And we know that at the bottom of the slide, our happy child now, who apparently stands up on the slide, is going at 1.8 meters per second this way. Okay, well, we know that heat is equal to mc delta T. We were told that it was iron, so that's going to be useful in the specific heat. So to find our change in temperature, all we know is that heat divided by mc should give us that value. The problem is right now we don't know what the heat is. We do know the mass and we do know the specific heat, but how in the world are we going to find the heat? And the answer, my friends, is that it's time to get into conservation of energy. And if you think about conservation of energy, remember that our energy initial is going to equal our energy final. And let's think about our initial energy. Sitting at the top of the slide, nothing's happening. We always wrote it as kinetic energy plus potential energy, but of course the kinetic cancels out because there is no velocity. And if we say equal, we again know that there has to be some kinetic energy, and we would always list this idea of potential energy final, but again, depending on where you establish your horizontal level, we can cancel that out because again, they are now no longer at some height off the ground. However, there's something different that we're going to add in here, and I'm going to go ahead and do it in a different pen color. Let's go ahead with fancy purple. And that's this idea that this time in the system, we're going to generate some heat. And if you think about this, really that makes a lot of sense, is that we're taking the initial potential energy and we're converting it into some kinetic energy, but also some heat. The slide heats up because we've gone down it. So if we take a look at this equation now, we can start to plug in some values. We know this is mgh, and we know this is 1/2 mv squared, and then we're going to add some q. You notice how I don't have any equation on here yet, because really we figured out from the initial solving of this equation over here that we're looking for q. So if we solve for q, what do we get? I'm going to mark that as initial, I'm going to mark that as final to make things clear. Well, q is equal to mgh initial subtract 1/2 mv squared final. Well, this should make a lot of sense to you because we're conserving our energy. Our heat is taking the potential, subtract the final kinetic. That should make a lot of sense because that initial potential energy is supposed to be the sum of these two. So if we start plugging in our values now, we know that this is a 35 kilogram person. We know that acceleration due to gravity is 9.8. The initial height was 3.2 meters. And we're going to subtract 1/2 times. There's that 35 again. And we were told, so thankfully, that at the bottom, they were traveling 1.8 meters per second squared. So, if you do all the math right, you should end up with a nice heat of 1,041 joules. So you see that the real trick to this is realizing that conservation of energy is certainly at play, and we have to use it. You can imagine this being even harder if I bring in the idea of conservation of momentum as well. So if we look back to our equation for delta T, we have our Q now, it's 1,041 joules. We still know our mass is 35 kilograms, and we know our specific heat, thanks to our table, is 460 joules per kilogram degrees Celsius. And we finally get a change in temperature of 0.19 degrees Celsius. Now, notice that this doesn't take into account what the initial temperature is or what the final temperature is, just that based upon the amount of heat generated from this transfer of energy from potential to kinetic and obviously to the substance itself, the temperature of iron is going to change by 0.19 degrees Celsius. So that's a little trickier, my friends, and as you go through these questions, realize in a lot of cases you're going to have to deal with similar ideas like this where conservation of energy is going to matter. So tricky stuff. Good luck in what you're doing with this sort of stuff, and we will talk to you later.